So there are some periodic trends besides valence electrons. And so we're going to talk about a couple of those. One is atomic size, the size of the atom. We can predict relative sizes just by position on the periodic table. So we can think of atomic size as being the distance between the outermost electrons and the nucleus, sort of like a radius. As we go across a period from left to right on the periodic table, the atomic size gets smaller. That's not what you would expect, right? You look at sodium has 11 protons, 11 electrons, and then chlorine has 17 protons and 17 electrons, and it weighs more. We expect that it would be larger, but it's smaller. The reason for that is, as we're going across a period and you're adding electrons to make larger atoms, they are being added into the same principal energy level. So going from sodium to chlorine, you're adding electrons in the third level. Those are all roughly the same distance from the nucleus, so that's not going to make them larger. But the number of protons in the nucleus is larger, and so that pulls those electrons in closer. So if we look at sodium, sodium has 11 protons in its nucleus. And then out here, it has 11 electrons. And then if we go over and look at, say, chlorine has 17 protons and 17 electrons. We have negative charges and positive charges. They are attracted to each other, and that attraction depends on the magnitude of the charge and also the distance between them. So here we have electrons that are roughly the same distance. The outermost ones are in the third level, and we have a charge of 11 on the nucleus. Over here, these electrons are also in the third level, but now the charge on the nucleus is 17. And so these electrons are more strongly attracted to the nucleus, so they get pulled in. So as we go across the periodic table, the nuclear charge increases and pulls those electrons in, and they get a little bit smaller as you go across. Going down a column, atomic size increases, and this one makes sense. You think about lithium with 3 protons and 3 electrons, or cesium with 55 protons and 55 electrons. You'd think, well, cesium must be bigger, and it is bigger. As you're going down, the electrons are going into larger and larger shells, higher and higher floors in the quantum hotel. And so the larger shells are farther from the nucleus, and so the atom is going to be larger as well. So here we have a chart showing relative sizes. So as we go from lithium, well, we were talking about sodium. As we go from sodium across, we see that the elements get smaller. Not what we would expect, but they get smaller because the charge on the nucleus is increasing. If we go down, they get larger, and that is what we expect. So there will be questions like this on the exam. Choose the larger atom in each pair, PB or PO. So you find them on the periodic table. There's PO, and there's PB. So what's the trend? As we go across from left to right, are they getting larger or smaller? Smaller. So they're getting smaller going across. So that means polonium is smaller. That means lead must be larger. So it's asking us to choose the larger. So lead is the larger one. Does that make sense? Let's do one that's a little confusing. Let's do C, tin and bismuth. Oops. So SN and BI. So here's SN and here's BI. Now this one's a little trickier because they're diagonal in the periodic table. So look at the two trends separately. So as we're going across, they're getting smaller. That would predict that bismuth is smaller. But the trend going down is that they get larger, and that one predicts that bismuth is larger. So those two contradict each other. This is an unfair question for Chem 3A. So can't tell on this one. If you have one like fluorine and selenium, so this one I'm going to say, don't know. Fluorine and selenium. Here's fluorine, and here's selenium. Trend going across says that fluorine is smaller. Trend going down says that fluorine is smaller. The trends agree, and so we can say that selenium is larger. So you should be able to answer questions like that. Ionization energy is another trend. That's defined as the amount of energy needed to remove an electron from an atom. So to make it into an ion by removing an electron. Ionization energy is opposite to the atomic size. So it increases as you move across to a period because it's harder to pull an electron off of a smaller atom because those electrons are closer. Another way to remember this is to think about, well, if I take an electron away from a group 1A element, that's actually going to make it pretty happy because group 1A elements like to lose an electron because then they have a noble gas configuration. So that should be pretty easy. Group 7A element wants to gain an electron to get a noble gas configuration. So it's not going to be real happy if I try to remove an electron. So as we go across the period, it's harder to remove an electron. Ionization energy increases. Ionization energy decreases as you move down because the outermost electrons, the ones that you're trying to take off, are farther away. So here's one of my non-politically correct analogies. So I have 6 children. I have a friend who only has 1 child. So if we were to go to the Fresno State Fair, the big Fresno Fair, I would have a hard time keeping track of 6 children. This is why I didn't go to the fair with 6 children and why I still have 6 children. Because you can imagine some poor lady with 6 kids at the fair, it would be really easy for someone to take one of them, right? Because you can't keep them all close. You can't even hold on to all of them. So big family, easy to take a child. Large atom, easy to take an electron. My friend with 1 child, she's going to walk around holding that kid by the hand. There's no way you're going to get that kid. Mom's got her eyes and her hand on him. You can't get it away. So small atom, harder to take an electron. Small family, harder to snatch a child. Right? If you took one of my kids, I might not even notice for a while. They're bigger now, so they'd fight back. So here's trends in ionization energies. So as we go across, it becomes harder to remove an electron. Ionization energy increases. As we go down, it becomes easier. Ionization energy decreases. So the trend here is exactly opposite to the radius. Let's just do one of these. Let's just do the first one. So choose the element with the higher ionization energy, magnesium or strontium. So again, find them in the periodic table. Here's magnesium, here's strontium. So if you're good at remembering things, you say, well, the trend is that as we go down, ionization energy decreases. I'm not good at remembering things like that. I have to reason this one out. I remember the size, and then I think about it. So the size, magnesium is smaller than strontium. As we're going down, this one has electrons in the 3rd level, this one's in the 5th, which is bigger. So strontium is bigger. So strontium's electrons are way out here, and magnesium's are closer. it's easier to take an electron from strontium. So it's a lower ionization energy. So then magnesium has the higher ionization energy. Any questions? Metallic character means how much like a metal is this element. It's a little bit like masculinity, right? So you can be a male, but some males are more masculine than others, and some females have some masculine characteristics, right? So we have metals and nonmetals in the periodic table, but they differ in how metal-like they are. One property of metals is that they lose electrons, and in reactions, and nonmetals gain electrons. As we go across a period, ionization energy increases, meaning that the electrons are less likely to be lost. So as you go across, the atoms are not going to lose electrons as easily. We see that metallic character decreases as you go across a period. It increases as you go down. It follows the same trend as atomic size. So that kind of fits with, typical gender stereotypes that typically a man is larger than a woman. So if you think of metals, I think of metals as being masculine. I'm not exactly sure why, but it works in my weird chemistry land. So if the metals are masculine, then the larger ones are more metallic. There's actually an even easier way to think about this. So we've got this stair-step line here, right? And we learned that separates the metals from the nonmetals. So here we've got the metals, and if you have a hard time remembering, well, iron. Is iron a metal? I think that should be just like common, you live on the earth type of knowledge. Iron is a metal. What about something like oxygen? Is oxygen a metal? No, I think we all know that. Oxygen is a gas that we breathe and is necessary for life. So these are the nonmetals, these are the metals. If we start drawing some lines and say we go on this period and go across, here we're going from metals, metals, metals. In between are the semi-metals, and those are the nonmetals. As we're going across, metallic character decreases, right? We're going from metals to nonmetals. If we go down, we're going from nonmetals, semi-metals, metals. So going down, metallic character increases. That make sense? Let's do B, just because I don't think I've done a B example yet. So silicon or tin, which is more metallic. So there's silicon, and here's tin. Which is more metallic? Tin. This is a semi-metal, and that's a metal, right? Going down, metallic character increases, so that's more metallic. Any questions?